Hey everyone, my name is Matt Rolchigo. I work at Oak Ridge National Lab. I'm the lead developer of ExaCA, which is a cellular automata code that uses Kokkos. It was developed originally as part of the Exascale Computing Project for additive manufacturing grain structure predictions, and I'll be talking about its performance and scalability using Kokkos. So a little bit of background of like what this code is actually doing. Essentially, when you're 3D printing these parts out of metal, especially really complicated geometries and complicated scan patterns where you're using a laser to melt metal, and you're looking at the properties of the parts that you have, the structure that forms during solidification ends up being pretty important for what properties you get out. And because that solidification structure varies locally based on the heat transport conditions, it's something that we would like to predict because, like I mentioned, depending on what the structure looks like, it's going to affect your properties. And so what ExaCA is doing is, given time temperature history data from a heat transport model, the form that we have is basically you have a regular grid discretized in space. You have a list of locations in X, Y, and Z, and you know when those locations heat above the liquidus temperature, cool below the liquidus temperature, and how fast they cool from the liquidus temperature. And we're trying to look at what the effect of the repetitive melting and resolidification does on the grain structure, where the grain structure is essentially localized regions of crystallographic orientations during solidification and the distribution of how big those are and how strongly textured it is. Are you favoring certain orientations over other ones? So initially you have some procedurally generated grain structure where each voxel is assigned to one of these grains. And after running ExaCA with this time temperature history, you get a new predicted grain structure. ExaCA uses Kokkos for parallelization as well as MPI and the JSON library, but those are its only dependencies other than CMake. There's additional post-processing you could do. I won't get into that. But the core of what ExaCA is doing is here. So it's kind of unusual because ExaCA isn't we're not really doing a ton of math. We're not solving big systems of differential equations. It's a lot of iteration over cells that all have states. There's a lot of memory access. There's a lot of load imbalance. So it's a more unusual application for something like Kokkos than some of the codes that you've seen presented here, where there's a lot more math that you're doing per atom, per location. But you start with a domain where all of your cells are assigned either the solid or the temporarily solid state, depending on whether it has one of these time temperature history tuples from our input data. If the cell is temporarily solid, once we step forward in time until we hit the time at which that cell is assigned a melting time, in which case it turns into liquid. The liquid cells can become active through one of three processes. The active cells are the cells where most of the work is being done. The interface is being tracked in those cells. But when those cells no longer have any liquid neighbors, that cell is then going to be assigned to either, again, the temporarily solid state or the solid state. So you can immediately see here that these active cells are only a small portion of your domain because you're melting this with a laser. Your parts are pretty big. You're really solidifying a small region on a given time step relative to how big your parts are. And these active cells, meanwhile, you're stepping over time, but there's also not that much work that needs to be done per time step. There's an interfacial response function where you're essentially calculating the interface size that are represented through these octahedral geometries. So you can get the local undercooling from your time and the cooling rate, and you could track the size of this octahedron through some other function, but this function is usually something pretty simple like a polynomial. But it's important from the physics side of things because it's linking your local solidification kinetics to the real time temperature history of that location in your part. But these octahedra, these update operations, and then these update operations for the liquid cells turning to active, this is where most of the work is actually being done. And so these three processes, as I mentioned, nucleation is the creation of a new active cell from what was previously a liquid cell if that cell reaches a predefined nucleation undercooling temperature. So not every cell is going to be assigned a nucleation event or a potential nucleation event, but this is basically you're creating a new octahedral envelope and changing that cell from liquid to active. Cell capture is the means in which an existing active cell triggers the creation of new active cells next to it. So if you have different cells that have certain grain IDs, those grains can grow as your liquid cools down. And that's handled through geometrical calculations regarding these octahedra, where a cell center is on one of these octahedral faces, and it involves creating a new octahedra for the new active cell. And then finally, activation. That's simply what happens as the region of your simulation that's superheated becomes undercooled. There's always active cells separating undercooled liquid cells from solid cells. So that is, again, similar to nucleation. It's the creation of a new octahedral data structure and the transformation of that liquid cell into an active cell. So in addition to the fact that this is a little bit unusual in terms of how little math is being done per time step and how many time steps we have, here's an example of a simulation being performed. So the blue is the liquid. All that time temperature history is coming from another model and being reflected on the CA grid, but you could see the grain structure that we had initially is now different because of the fact that we had these competing nucleation and solidification processes where octahedral envelopes from active cells were claiming new cells and so on as you finish solidification. But there's certain unique challenges here for having a CA model that's scalable and performant on GPUs. There's a large number of cells and a large number of time steps, but at the same time, as you saw from that flow chart, most of the work is being done in the undercooled liquid cells and the active cells, which are, at a given point, like a very small portion of your domain, pretty much just the tail end of this blue region, and then 1 to 2 sets of blue cells at the edge of your solidification microstructure. And not only is your work imbalanced on a given time step, and you have a lot of time steps, but also the location of where those cells are is constantly changing. So we do use MPI parallelism, where this is broken down into spatial chunks, and each chunk communicates the state of cells from adjacent chunks. But even then, because of the fact that the mel pool is in one spot, the static MPI domain decomposition doesn't really give you that much in terms of strong scaling. But I'm going to point out some of the things that we've done over the years to speed this code up, and what worked and what didn't, essentially, for just this raster test problem. So most of our development was during the ExaAM project, so during the Exascale Computing Project, but then since then, there's been a few random things that I've tried over the years that have improved our code a lot. But when you look at where we were back when ExaCA was first released, version 1.0, we're significantly faster, especially on CPU for this problem, as well as around 3 times faster on GPU than when we started. So this is all running on one node, 54 MPI ranks on CPU, 8 MPI ranks on GPU. But you can see that most of the changes that we've made can kind of fall into one of these general categories. The pink changes, especially on CPU, just improving the branching logic. There's obviously, when you look at the structure of the code, you can see that there's a lot of if statements and a lot of algebra. So just things like using Kokkos subview to avoid having to index where your cell is relative to the current layer of the printed part versus all layers, and using the Kokkos math functions ended up being a pretty useful thing on CPU. Inlining repeated calculations, a lot of these steps are things like create a new octahedron and calculate how big it needs to be to capture all its neighbors. Things that are done in multiple spots in the code, for example, in both nucleation and activation, using Kokkos inline functions ended up being pretty useful for things like that on GPU. One thing that's helped us in both is the fact that we know the time temperature history in advance, just leveraging the fact that we have that to say, look, we know we have to do a lot of iterations over these cells, but we can reduce the number of iterations because we know when things are going to go above and below the liquidness in advance. So we know what possible transitions are possible for a given cell on a given time step before we get to that time step. The Halo exchange, the MPI communication ended up being a significant bottleneck, and trying to improve that helped us. And then there's one thing that actually slowed us down. That was just adding a new capability that we ended up clawing that performance back on both CPU and GPU. But originally, essentially, the main loop, the main thing that we're doing in this code is we're doing a Kokkos parallel 4 over all the cells. And If you were a solid cell, you can turn into a new liquid cell if we went above the liquidus. If we're an undercooled liquid cell, we check to see if activation needs to occur. And if we're an active cell, there's this procedure of updating my octahedron size, checking my 26 neighbors to see if any of them are liquid and my octahedron is big enough to engulf them. If it is, there's a Kokkos atomic compare exchange so that we don't operate a capture event on two cells at the same time. But then if we do have a successful cell capture event, we have to generate a new octahedron, do a bunch more calculations, and then we need to check for the active cell turning into solid criteria. So you could see just from this being essentially what the code looked like back in 2021, that there would be a lot of thread divergence. Whichever thread ends up with that small portion of the domain with all those active cells, that is going to be that's going to be what's limiting your code. So really the fact that there's not many cell capture events on a given time step, but one thread might end up with a lot of those, made it so that we really needed to use the known time temperature history to optimize this kernel for efficiency. So this is essentially what the code looks like now after those optimizations. So I know we were running a little bit behind, but how much time do I have?
We have 8 minutes.
Okay. So we end up breaking down that one update kernel into these three. So we have now 3 parallel 4s instead of 1, but each parallel 4 has significantly less thread divergence. So the first one, remount activate cells, we're only iterating over the cells that are going above and below the liquidus on that time step. So we've sorted all of the time temperature history chronologically. So we look on this time step, how many things are happening. Usually it's not many, it's a handful. So really there's some wasted GPU performance here because you're only iterating over a couple things. But here we could perform the remelting and the activation operations. Or what we actually do is we have a steering vector of things that are going to happen on this time step, and we do an atomic fetch add and update the location of these cells on the steering vector. So we don't want to do that much work because we know that there's going to be thread divergence, but we want to basically mark the cells that matched the criteria for one of these two things happening, remelting or activation. Filling the steering vector, so here we actually do iterate over all the cells in the system, but all we're doing is looking for the ones that are active and undercooled, and we're again doing an atomic fetch add to this steering vector. And so the steering vector is essentially a list of the 1D indices of the cells where more work is going to need to be done. And finally, the cell capture, we're now not iterating over all of our cells. We're just iterating over the ones in the steering vector, which we previously identified as either going to undergo one of these transitions and has to have an octahedron size being updated and the check for the cell capture of any of its neighbors. By doing this ended up helping us a lot in the code. You could see we use some of these atomic operations to add things to the steering vector, in addition to the compare exchange when we do the cell capture event. But despite the fact that we have more atomic operations and more parallel 4s, by forcing most of the work to be done in one kernel and having these two pretty simple lightweight kernels without a lot of if statements ended up really helping us. And this was possible because we knew that time temperature history in advance. The halo exchange routine, previously we were kind of sending chunks of cells. So if we had a 1D decomposition, we were loading in all of the data for cells that got updated into a position in this vector that's size nx times nz if it's decomposed, for example, in the y direction. So you have a grain ID, you have an octahedron center, an octahedron size, and based on where it is in the buffer, we know the x and z location. There's an MPI, I send, I receive, and then we go ahead and unpack this buffer by iterating over it, seeing which cells were updated, and then updating them on other ranks. The issue here is that, as we saw earlier, there's not that many not many of these cells are actually being updated per time step. So the fact that we're iterating over all nx times nz of the cells every time step at every MPI boundary, but there's a small but also varying number of those cells that are being updated on a given time step. This ended up creating a lot of iteration over things that weren't happening and thread divergence. So what we ended up doing was having a guess at how many events we would have on a given time step that would need to be communicated across the ranks. We were able to reduce this from double precision to single precision by breaking down some of these numbers into essentially components, smaller components. And while there's now more components, we were able to reduce the size of this buffer by replacing the initial size of what's the max number of cells that might be communicated with a guess. So there's an additional thing where we have to check to make sure all the information fit in the buffer and resize those objects. But if your initial guess is somewhat reasonable, just having to iterate over this n cells, much less than nx times nz or nx times ny, ends up saving us a lot of performance, because a lot of times, even though we have more kernel calls, we're saving a lot of thread divergence iterating over just the number of cells that we think might have transformed. There's still challenges with strong scalability due to the inherent nature of this problem. So you could see the performance has improved, but the strong scaling for the AM problem really hasn't been. And that's again due to the spatial load imbalance. There's not really that much that has to be done per time step. So no matter how much you chunk that up, you're really, without a time parallel method, you're not going to be able to get really good strong scaling out of this kind of a code. For directional solidification, which is a more symmetrical problem in X and Y, we are able to scale up to hundreds and thousands of nodes of frontier pretty effectively with the current version of ExaCA, though previous versions weren't very good with strong scaling even for that problem. So the main takeaways, since the initial release of this code about 4 years ago, we're significantly faster on CPU and GPU for these problems where we're modeling the grain structure of 3D printed metals. The most significant obstacle that we faced to the performant and scalable calculations was the load imbalance among the threads and the ranks. We found that doing more for loops and more iteration per time step can improve your performance counterintuitively as long as you've improved the load balancing. Leveraging the known temperature history of this problem saves us a lot because we're able to intelligently only iterate over things that we know are likely to happen. And then because there's just a limited amount of work to perform per time step, that's always going to limit their scalability for a problem that requires a lot of time steps without a time parallel approach. There is a time parallel CA that's coming out, going to be open source released from Oak Ridge called Toucan. That will probably be around sometime this summer if you guys want to check that out. But here is the GitHub link to this code. It's open source if you want to check it out. I know it's kind of a weird thing to explain because there's not a lot of math and there's a lot of if statements and branching logic. So actually looking at the code might be more useful than looking at my flowcharts. But reducing the branching logic complexity and streamlining the math really helped us on the CPU. Inlining repeated code helped us a lot in the GPU. There's some Kokkos features that could help, like having the steering vector be built-in functionality. We actually don't really do any iterations over the entire chunk of cells, but things that improve multidimensional view access could also help, because right now all of our views are 1D structures where we unpack and repack the loops. But anyways, thank you for listening. Happy to take any questions.
Thank you, Matt. Maybe time for one quick question while Daniel is setting up.
Have you looked at how many things are actually gonna do this atomic insert into the atomic add into the steering vector? Is that a large fraction or is it a very, very small fraction?
So it's a large number on a given time step. Like it might be on the order of hundreds, but the number of cells that you have on a given MPI rank is usually on the order of something like 10,000 plus. So it's a small fraction of the cells you have available, but it's more than just a few cells. We've tried keeping the steering vector between time steps instead of rebuilding it every time, but...
No, yeah, I was just wondering if it's just like, if you have a 1% hit rate or something like that, and, it's just like 100 elements, atomic adds are probably the right way to go. I was just wondering, if something like parallel scan, etc., would work better, but for very... for small fractions like that, atomics are the way to go.
Okay.
Pretty sure.
We did try parallel scan at one point as well to build the steering vector, but for this code, it didn't really help us.
No, I wouldn't expect it.
Yeah.
All right. I think we'll just put any other questions in the...
I have a
Okay, well,
I'll try and be as fast as possible. So I was wondering with the load balancing issue, if it seemed to me that the problem had like a lot of element of persistence with the load balance, like elements would sort of tend to be active over consecutive time steps, even if they would deactivate later. Like I was wondering if you have explored using any kind of like dynamic load balancing strategies that would kind of like use previous time steps for predicting the load on the new time step.
So I think we try a couple different ways because we had the same thought. Most of the things in the steering vector, they're an active cell. You're updating the octahedron size, but it's going to be relevant for the next 30 time steps. So instead of rebuilding it every time, what if you just maintained a steering vector? I think the challenge was at some point you don't need it anymore, so you have to keep track of like which things in your steering vector need to be removed. If you like try to clean it up like every 30 time steps and then just like reorder everything, you end up just slowing your code down because just rebuilding it every time ended up being faster. There might be a way to have it be persistent, but the challenge of having to rebuild it, like every time step was faster, not rebuilding it, but then when you do have to rebuild it, that ended up hurting you enough that it wasn't worth it.
I see. Thank you.
thank you, Matt.